Okay, I think it's time to start. Welcome to this week's web seminar. It's my pleasure to introduce you to Lawrence Keek. He obtained his PhD from Utrecht in the Netherlands, and right now he's working at the X-ray laboratory of NASA. And his talk today is going to be on thermonuclear bursts. So whenever you're ready, please start.
Okay, thanks so much for the invitation to talk to everyone on this online seminar. So I'm usually at NASA Goddard these days, but actually right now, today for a symposium, I'm at my official employer, which is the University of Maryland. Probably can't tell from the backdrop. I've just finished a paper on a very long type 1 X-ray burst that went off just about a year ago. I think it was November last year. And so I thought that that would be a nice thing to discuss. I'm all excited about it. Although I just received the referee report, so I'm now very frustrated. To set the stage, let me just show you my usual, the usual artist impression that I always show of a low mass X-ray binary. So here we have a neutron star hidden in an accretion disk, accreting hydrogen or helium-rich material from a companion star. Now, accretion can go on for quite some time, and you form a layer of hydrogen and helium on the surface of the neutron star. And because of that star's strong gravitational pull, that material gets quickly compressed to the point where thermonuclear fusion starts. And when this proceeds as a thermonuclear runaway, then fusion engulfs the star as a flame within a few seconds, burning all the hydrogen and helium that is present there, and that powers a very bright bursts of X-rays. So in the right-hand figure, you see an example X-ray light curve observed from such a system, where you see within a few seconds the X-ray flux increase dramatically. And then over the course of 10 seconds to a minute, you see the neutron star cool down again. Such X-ray bursts are quite common. We've observed thousands of them since the 1970s. Now, when I show you an artist impression of such a binary star system, that's actually not what we usually observe, because we can't resolve these sources. They're just point sources to our X-ray telescopes. And so most of the information about the geometry of such a system comes from the spectrum. And last week, just for fun, I made a spectrum of the artist impression. And you see there that two colors stick out. There's lots of red and yellow from the companion star and from the accretion disk. And there is this bluish shine coming from the neutron star. And in the case of this picture, the artist also drew in a powerful jet. I think jets are present in these systems, but they're typically not thought to be extremely powerful. In the X-rays, you similarly see in the spectrum these two components, one from thermal emission from the neutron star and another from the accretion disk. You typically only see the hottest part of the disk, the inner part. You don't see the outer parts and the companion star. And another issue with an X-ray spectrum is that here in this fake spectrum, the two components are nicely separated, so you can see what belongs to what. In the X-rays, they will overlap, and it becomes more difficult to disentangle the emission from different emission sites. Now, during an X-ray burst, the component belonging to the neutron star, a black body for thermal emission, will be the most powerful component, and it will dominate the spectrum. And so it becomes more difficult to see what is happening to the other emission sites, such as the inner accretion disk. Typically, these X-ray bursts are quite short. So here are some example light curves. On the left, there is a a typical XMM light curve of half a day, where you see several of these short X-ray bursts that last at most a minute. And you see that every few hours you accrete a new layer of fuel, and you burn that, and then you continue on to accrete the fuel for the next burst. And during these short minute-long bursts, you don't really get enough photons to disentangle the two different components in the X-ray spectrum. There are some rare bursts that last much longer. On the right-hand side, you see an example of that. That's a superburst. So you have a similar fast rise of the X-ray flux, but this time the cooling of the neutron star takes hours, up to the better part of a day. In this case, we think it's not hydrogen and helium burning that's powering the burst, but we think that it's a deep layer of carbon that is producing the energy to power this X-ray burst. So it's a different type of fuel, igniting much deeper, and the burning of the cooling down of that thick fuel pile, that takes quite a bit more time. And in that time, in principle, you can collect many more photons. And so you have more detailed spectra. Now, unfortunately, because these long bursts are so rare, usually you don't pick them up with a very sensitive X-ray telescope. They're usually picked up with all sky monitors that, again, don't record that many photons. And so there's only a very few of these long bursts where we have detailed spectra, and where you can actually start looking in detail at different components of the spectrum. Now, to show you schematically where this all happens in the neutron star, the larger part of a neutron star is taken up by its core. That's the most mysterious part. That's what we're all after, to figure out what it consists of, where it really is a neutron star, or maybe the core consists of quarks, and we should really speak of a quark star. And on top of that, we have this solid layer, or a crystalline layer called the crust. And all the X-ray bursts that I'm talking about, the short ones and the long ones, they all happen within the top 100 meters of the star. So accreted hydrogen and helium forms an atmosphere of just a few meters. And so when you see a short burst, those ignite at the bottom of the atmosphere. And the burning of hydrogen and helium leaves behind a thick pile of ashes, forming a liquid ocean of about 100 meters. And these superbursts, these long carbon flashes, they ignite near the bottom of the ocean, close to the crust. So that's interesting, because when you see a superburst go off, you know that close to the crust it must have been hot enough to ignite carbon. So it's a probe for the thermal properties of the outer crust. Now, there's one other way in which you can get a long burst, and that is if you have a very cold neutron star. And if you're accreting a very thick pile of helium. So if you have a cold neutron star, then you can accumulate a thicker pile of fuel, for example, helium, before it goes off. And then that thick pile of helium might also power a longer X-ray burst. Typically, they're not as long as superbursts. They don't last hours. They maybe last half an hour. There may be some overlap in the two categories. I'm saying there can be some overlap because we've seen some very long bursts from cold neutron stars. This is an example of one from the globular cluster Tews 5, where this particular neutron star was not accreting for a long time, and we think that they can only heat up during accretion. So because it wasn't accreting for a long time, we thought it was cold, but still we saw this few hour-long bursts go off a few years ago. And only after that superburst did accretion start, and did we have an episode of accretion for a few days. Now, the data in this observation is quite crude, and we don't really see the start. So we don't really see the properties of the star of the onset of the burst that could distinguish between a carbon flash or a helium flash. And so this would either be an extraordinarily long helium flash, or it would be a carbon flash from an unexpectedly warm neutron star, even though we thought it should have been cold. And so in recent years, we've seen a few of these examples of what look like carbon flashes, what are long X-ray bursts, but from sources that are supposed to be cold. The latest example of a long flash from a neutron star accreting at a very low rate, so supposedly cold, is the burst that I've been studying over the last year from the source with this nice name. It was first discovered with Integral in 2006. And so this figure shows you the X-ray light curve as seen with two instruments. On top is the Burst Alert Telescope on the SWIFT satellite. And at the bottom, we see the signal from this source as detected with the MAXI all-sky monitor that is a Japanese instrument on the International Space Station. And so in 2006, this source started accreting. And from about 2010, that's roughly also when MAXI was installed, you see that it has been emitting X-rays at a very steady rate, albeit a low rate. It's accreting at about 0.1% of Eddington. So that's 2 orders of magnitude lower than what you see from the more prolific X-ray bursters. So we think that because of that low accretion rate, the neutron star would not have heated up much. Now, 2 X-ray bursts have been observed from this source, both of them longer. One in 2012, and the other one, the one that I will be discussing in detail, is the one from last year. And in the meantime, there were some detailed observations with the Chandra and NuSTAR observatories, where they looked at this source when it was not undergoing an X-ray burst. So those spectra probe what the system looks like when it's not undergoing a thermonuclear flash. So the first thing that I'd like to do is look at those spectra and see what we can learn about the accretion environment around the neutron star. This data has also recently been published by Nathalie Degenaar and collaborators. Apparently we were working on it at the same time. So at the top you see the data, the spectral data from Chandra and NuSTAR, and I also include MAXI. I've been looking at that source for a long time, but it's not collecting as many photons as Chandra and NuSTAR. And in this spectrum, there are these 2 components that I've talked about. So there is a thermal component for the neutron star, showing that it's indeed a colder neutron star. The blackbody temperature is just half a keV. And there is another component that's well modeled by a simple power law. This is likely not the inner accretion disk itself, but it's likely coming from a corona of hot electrons around the inner disk and the neutron star, which may be upscattering some of the thermal emission of the neutron star. In the second panel, you see a fit with such a simple model of a blackbody and a power law to the spectrum. And it describes the data for the most part, but you still see some things sticking out. There is this emission line around 6.5 keV, and there is this whole hump of emission above 20 keV. And then when you look at the soft X-ray band around 1 keV, you still see some lines or some features sticking out. Now, this collection of features is something that we see in other sources as well, and this is typically associated with X-ray reflection. This can happen when one of these 2 components, in this case the power law, which is now the most powerful emitter, Some of that emission comes directly towards our telescope, but part of that emission will be intercepted by the accretion disk and reflects off the disk. Reflection in this case is not reflection like in a mirror, it's more of a diffuse scattering. And in the process of this scattering, some of the emission is being reprocessed, and that introduces some features into the X-ray spectrum that carry information about the reflection side. So here is a model of what a reflection spectrum would look like. So the gray shaded area bounds at the top a black body, and the other lines show models of reflected black bodies. And you see that those models above about 2 keV, they don't show much difference. They're quite similar. For instance, around 6.5 keV, you see this emission line that we also saw in the observed spectrum. That's an iron fluorescent line. So that's iron in the accretion disk that is lighting up and producing this line as it is being irradiated. The hump above 20 keV, you can't really see that clearly in this model. That's because of the choice I made for the temperature of the black body, but it's in there, it's in the models. And you also see that in the soft band around 1 keV, there are also these lines sticking out, similar to what we saw in the observations. But here, at that part of the spectrum, the different models give quite different predictions of what the reflection spectrum should look like. And these are different models for different compositions of the reflecting material, hydrogen or helium. And more importantly, for different densities of the reflecting material. So if your accretion disk is much denser or less dense, that will determine how prominently these lines stick out from a reflection continuum, which is a Bremsstrahlung continuum. So especially in the soft band, there's lots of information that you can extract about the reflecting medium. Now, I fitted such a reflection model to that spectrum. That's the bottom panel. And you see that those reflection models describe the iron line quite well. That's completely disappeared from the residuals. For the most part, the hump, it's called the Compton hump, is described. But below 2 keV, there is still some residual wiggles that you can see, some lines that are not fit that well. And one unfortunate thing is that although there is so much information in the soft X-ray band, the current reflection models only assume one particular density, for instance, and one composition. And that's just because it's very expensive to calculate these models. So in principle, you would like to have a huge grid that covers the entire parameter space. But at present, we don't have such a grid yet. So things not fitting correctly in that part of the band, I think is not an indication that the reflection interpretation is wrong. It's just a sign of how much more information is still there that we can't probe at present. Now, some of the information that we can't get out of there is, for instance, the location of the reflection. Reflection usually is assumed to occur of the inner part of the accretion disk. And in this case, from the width of the line, you see that the line is not that strongly broadened, so it was not very close to the neutron star. And myself and also Nathalie Degenaar found the reflection side was about a few hundred gravitational radii away from the neutron star. So usually accretion disks extend up to close to the neutron star, but in this case we find that it extends, that it has been cut off far away from the neutron star. One gravitational radius is about 2 kilometers, I believe. So this is a few hundred kilometers away from the neutron star. So that's quite different from the artist impression that I showed you, where the disk was coming close to the neutron star. Another striking thing that we find from this is that the material is highly ionized. And the ionization is usually parameterized as an amount of flux that the disk receives per particle. So it's proportional to the illuminating flux, F, and inversely proportional to the number density of the reflecting material. Now we find that this ionization parameter has a high value, even though this is persistent emission at 0.1% of Eddington. So this is a very low persistent flux. And still the ionization state is high. So usually we couple the ionization to mostly to the flux. But in this case, it might be actually that the density is much lower than what we typically assume for an inner disk. So maybe this is not the typical geometry for an inner disk that we expect, but some kind of more tenuous gas near this truncated inner disk. So that's the information that we can get about the surroundings of the neutron star while it is not undergoing an X-ray burst. And the interesting thing is now to see what changed when the X-ray burst went off. And we're going to look at the one from last year, which was the longer one. It was first detected with the MAXI all-sky monitor on the International Space Station. And we got a spectrum from that observation. And then 3 hours later, the SWIFT satellite slewed to this source and started observing it with its X-ray telescope, and also with its UV optical telescope. And here you see the two light curves on top in the X-rays and at the bottom in the UV optical with different filters. And it's on a logarithmic time scale. So in total, the observations lasted about a week and a half. The burst was observable for about a day. Then after a day, something dramatic happened. There was some dramatic drop in the flux, and then there was some kind of restoration to some value for the flux. One of the nice things was that this particular X-ray telescope has coverage below 2 keV. Most of the long bursts have been observed with instruments that are not sensitive in that energy band. This particular one is. And so we can also look at the reflection features, for instance, in the soft energy band. So let's look at the spectrum. Let's look at the spectrum just at the start of this series of Swift XRT pointings. So that's already 3 hours after the start of the burst. And you see the spectrum at the top, and the dotted line is a black body fit to this spectrum. So you see that where previously the power law was dominant, so this is this Comptonized emission from a corona around the neutron star. In this case, the dominant component is power law, the body of the neutron star itself. So that's clearly a neutron star that has been heated up by a powerful X-ray burst, and it's now glowing in the X-rays. Now still in the residuals, you see excesses at both low energies and high energies. The data quality isn't that great, so you can just fit one power law to it, and then most of the excess is fitted. You may still see some wiggles. The strongest one may be around 1 keV. You can put a simple Gaussian emission line there. Maybe that's a similar emission feature as what we saw in the persistent spectrum. Also in the bursts from 2012, a similar emission feature at 1 keV was observed. So you can fit the excesses of, over the black body with one power law, but I think that actually what physically is going on is that there are two additional contributions to this spectrum. The power law that we also saw in the persistent emission could come from the upscattering of the thermal emission of the neutron star, and so that would contribute the high energy tail. The low energy part, that could be this extra emission that you expect in the soft X-ray band from X-ray reflection. We don't see the iron line from X-ray reflection here. That's mostly because Swift XRT is not that sensitive at the energies where you would expect it. And also the illuminating flux there is not that strong because we are dealing with a already cooled down neutron star. This is already a few hours into the burst. But reflection would still contribute this Bremsstrahlung continuum to the X-ray spectrum, as well as some features around 1 keV. So what I did is I used that interpretation with reflection models and an extra quantization component to fit the burst spectra throughout the entire burst. And that gives us a picture of what is going on with the different accretion components as the burst goes off. So there are 3 times when we have some measurement. There is the persistent measurement that we had. There's a MAXI spectrum from the burst peak. I analyzed that, and then there is the burst tail, and those are the Swift XRT spectra that I just showed you. Now, at all times is the reflecting material highly ionized. That doesn't seem to change. But the location of reflection does seem to change. So during the persistent emission, the inner disk was truncated far away from the neutron star. And as a different type of artist impression, you can look at the one on the left, where instead of the disk coming close to the neutron star, the disk is now further away from the neutron star. That's what the persistent situation was. Now, during the peak of the burst, the MAXI spectra weren't of sufficient quality that we could measure that location. But in the burst tail, we could we could measure the location of the reflecting material, and it was quite a bit closer to the neutron star. In this case, only 10 gravitational radii away, with rather large uncertainties, but it's an order of magnitude difference. So that suggests that initially the disk is far away from the neutron star, perhaps held up by a magnetic field. And then as the burst goes off, for some reason, the inner disk collapses and moves closer to the neutron star. One process that could produce this is, for instance, Poynting-Robertson drag, where the drag of photons that are impacting the inner disk could cause them to lose angular momentum and fall in. Another interesting thing is that in the MAXI spectra that were not of such high quality, there was one thing that was quite clear, and that was that this power law of this hot high energy tail to the spectrum was not present there. If it would have been present and would have been as strong as during the persistent emission or the tail of the burst, we would have seen it, but it is not there. So that suggests that at the peak of the burst, where we also see photospheric radius expansion, that the corona was briefly disrupted, and then later on the tail it has reformed. So that's quite an interesting picture of how the environment around the neutron star is strongly affected by the irradiation of this powerful and very long X-ray burst. So now that we've quantified all the different emission components, let's look at what's going on in the neutron star itself. So let's look at the flux coming from the blackbody emission of the neutron star. And there you see it's a function of a logarithmic time axis. You see the first data point is the first MAXI detection, where we had radius expansion. And after that, over the course of about a day, you have straight power law decay. And the power is about -1. So the flux decays as 1 over time. That is roughly what you would expect for when cooling is dominated by the ions in the envelope of the neutron star. After about a day, the flux suddenly drops below the cooling trend. That's a bit mysterious. The dotted line indicates what the pre-burst flux level was. Now, in the pre-burst flux, the flux is dominated by the power law, whereas during the burst, it's dominated by the blackbody. So roughly here, where we have this strange drop in flux, that's where you would transition from the flux being dominated by one component to being dominated by the other component. So something is happening there that is making some switch, but it's blocking temporarily our view of the neutron star. Either that or suddenly the neutron star cools down quite a bit, and then later comes back up. Now, if you integrate the energy that you see being emitted here during this long burst, and you assume that it's powered by helium burning, then you get a fuel column that is about 5 × 10⁻11 gram per square centimeter. And that's the point where we start asking ourselves, is this a long helium burst, or is this a long carbon burst? Is it an intermediate duration burst or a superburst? Bursts that last a few hours are typically thought to be carbon-rich flashes, superbursts. But if you look in this diagram of ignition conditions, then around the ignition column of 5 × 10⁻11, if you go to the carbon curve there on top, you need quite a hot envelope to ignite carbon at such a relatively low depth for carbon ignition. Whereas the ignition curves for helium burning, they lie quite a bit lower. They lie around temperatures of 10 to the 8. So if this source is indeed colder, as what we expected, then the deep helium burst is the most likely scenario. A few weeks ago, when Sophie Hahn gave her talk, she showed some models of envelopes of different compositions around neutron stars and their densities. And one question was, what set the density, the maximum density for a helium envelope? And it was a bit unclear at the time, but you can see from these ignition curves that at a certain depth, the ignition curves curve downward. And that's where I think that is because of pycnonuclear effects. So at lower densities, at lower columns, it's mostly thermonuclear burning, and at some point pycnonuclear sets in. And so even when you're very cold at a certain depth, and actually that is not that far from where we inferred the ignition to occur, you will start burning anyway because of density dependence. Interestingly, this same ignition depth also indicates that if this were a hydrogen accreting source, that you're very close to the temperature where you would transition from unstable hydrogen burning and stable hydrogen burning. However, any hydrogen that would be there would have burned long before the helium flash would go off. So there's plenty of time to burn all the hydrogen to build up the helium-rich pile. an interesting consequence there is that because we have such a low accretion rate, gravitational settling would also become important, and that is not being taken into account in that figure. Okay, so this is what we could figure out about this one very long X-ray burst that happened last year. We could see all these. We could almost see all these effects on the components around the neutron star, coronae, inner accretion disks. But the spectra were not that detailed, unfortunately, mostly because the collecting area of the instrumentation was just not that great. Luckily, next year that may change. There may come some interesting observations sometime next year when NASA launches a new X-ray telescope called NICER. Stands for the Neutron Star Interior Composition Explorer. It will explicitly spend lots of time on neutron stars, X-ray bursters, but mostly also pulsars. And it will be placed on the International Space Station. So in the figure on the left, you see it's this box with an array of detectors that stands on an arm on the space station. And whereas for Swift XRT, we had this 3-hour delay before they could follow up on the long burst, NICER can more quickly slew to such bursts. They can slew to within a few minutes. So we would get much more data at the start of the burst, but also the effective area of the collecting area of this telescope is much larger. It's larger than XMM Newton. Swift XRT, I think, has an effective area of 100 or 200 square centimeters. So NICER will have close to an 18 times larger collecting area. That means that when you observe such a long burst, you will have 18 times more detailed spectra. But it also means that for shorter bursts, you might also already detect enough photons to do something similar in a short 1-minute duration burst, as what we could do now with this day-long burst. So this year I published a paper with David Valentine and a very enthusiastic undergraduate student at Georgia Tech, Zane Wolf, where we simulated reflection signals as observed with NICER from strong bursts, and as a function of the flux for 1-second exposures, or you could alternatively say as a function of the fluence of a short exposure, we calculated what the uncertainty would be in the reflection parameters. And we found that for a bright burst within 1 second, you can, for instance, constrain the ionization state of the reflecting material to 10%. So whereas now we've only been able to look at reflection signals for less than a handful of long bursts, hopefully starting next year, we will be able to do this for the many hundreds of bursts that you can see in reasonable times from many of the bursting sources in our galaxy. NICER is completely finished. It's been finished since, I think, June or July. It's now sitting at Cape Canaveral, just waiting for a ride to the space station. Unfortunately, it needs to hitch a ride with SpaceX, and one of the Dragon, is it the Dragon? No, it's Falcon 9 rockets exploded this year before launch. And so before they figure out what happened, NICER's launch has been put on hold. It's currently scheduled for March, but we'll have to see how that goes. My only wish is that it happens before the end of my postdoc. It will not happen before the end of my talk, because we're there already. So we discussed these long X-ray bursts from either thick piles of helium or thick piles of carbon that are interesting because they probe the thermal properties somewhat deeper in the neutron star envelope, close to the crust, but also because they allow us to collect more photons such that we can look at the interaction of a burst on its environment. And that's nice if you want to study accretion. It's also nice when you want to make sure that what you're comparing, for instance, to models of nuclear burning, that is purely the burst and is not some effect of the surroundings. Now, we've looked in detail at spectra from one particular integral source that had a very nice long burst last year, and we could see hints of interactions between the burst and the surroundings. We saw a corona that was blown apart by at the peak of the burst and then reformed later. And we saw that the inner part of the disk was previously held up far away from the neutron star, possibly by a strong magnetic field. And then, under influence of the burst, collapsed and moved closer to the neutron star itself. And our conclusion was that because we think this is a cold neutron star, that it must have been a thick pile of helium that ignited. And that would make it one of the most powerful helium bursts, I think, that we've observed so far. And I urge you all to stay tuned for nicer next year. So thanks for your attention.
Ow.
So thank you very much for this very nice talk. As usual, we have some time for questions. Please indicate in the chat if you have some questions.
I have a question. Can you go back to the slide with the structure of the neutron star with the crust and the liquid ocean?
Mm-hmm. Let's see. Yeah.
Great. So I'm wondering what the difference is between what we call liquid in the ocean and what would be more solid in the crust.
It's just a genus synonym.
So the state of the matter, of course, is the trivial answer. Usually when we model these things, well, let me answer it as a function of the composition. Mm-hmm. So the ocean is mostly the gaseous layer of the hydrogen and helium burning. So that's carbon, but mostly it's iron group nuclei. So it's mostly iron and some heavier stuff. When you go into the crust, you start having electron capture reactions, and you start changing that iron and other constituent particles into more neutron-rich isotopes. And so the deeper you go, the more neutron-rich you get.
Mm-hmm. Okay, that makes sense. Thank you.
Sure.
So there were a bunch of questions. Let's see who is next in line. So there was one who
Shall we start? As you?
Yeah, so that's a superburst. Wouldn't it be one of the shallowest ever observed?
Can you repeat?
Wouldn't that be, like, if that's a superburst from the integral source, wouldn't that be one of the shallowest ones ever?
Yeah, I think so, yeah. If that were a superburst. The only exception may be GX17+2, which had bursts that were also called superbursts. But that source is at Eddington, and probably those would have a very relatively shallow emission depth. I'm not sure what the value would be.
Okay, thanks.
Any other question here?
Okay, there was one more question by chat.
Okay, I'm just going to go ahead and ask one since I don't know who got one. So Lawrence, my question is, you note that the crust of the ocean is probably too cool to ignite carbon. would that still be true if you added in some mysterious shallow heating source that's roughly as strong as what is inferred for cooling transients?
That may be able to fix it. I don't know how much you would need here. You probably would need a lot, as in many MeVs per nucleon. Andrew Cumming has a nice paper in 2006 where he shows ignition depths as a function of QB and M dot. And I looked into that paper specifically. He has those figures for carbon flashes, but also for helium flashes. And I remember looking at it specifically for helium flashes. And if this were a helium accreting source, then it would already be difficult to explain the ignition depth. For a helium accreting source, he predicts that even if you have an MeV per nucleon, not sure how much of that goes into the core, but for a helium accretor, it would already be tricky to explain this helium burst. So I was thinking maybe this is a hydrogen accretor, and the hydrogen burns to helium, so it provides the helium, the fuel, as well as the heat that you would need to ignite it in the right spot. I'm not sure how much heating you would need to ignite carbon, but I'm very skeptical that you would be able to get that much. That's not very quantitative, but that isn't.
No, okay, thanks.
Well, I can do it.
Okay, maybe another question by Chuck.
Great. So I had two questions. One is, what's the density in grams per cubic centimeter for this deep helium ignition?
That's not something that I calculated for this specific case, but I guess it's around 10 to the 7 grams per cc.
I'm sorry, I didn't hear you.
My best guess is around 10 to the 7 grams per cc.
And that sounds very dilute for the thermonuclear.
Yeah, I must admit, I'm not. So these curves turn off, and I thought I remembered that it would be because of thermonuclear effects. But maybe I'm misremembering that. So it could be that it's another effect that's turning them over.
My second question is, what makes this system special? Is it just the very low accretion rate?
The very low accretion rate makes it special, but part of that is a selection effect, because at such low accretion rates, you don't expect to see burst often. I think there's only one other source where we have seen more than one X-ray burst at such a low accretion rate. The other thing that makes it special is because of the truncated accretion disk. And there's lots of discussion in the literature about what this might mean for the actual mass accretion rate. But that's more for the transfer from the companion star to the disk. In the X-rays, we see what's coming from the disk onto the neutron star, so that's a bit more robust. If you add up all the material that you see falling in from the X-ray flux, that is roughly the same column as what we infer that has been burned.
About the, hi Lawrence, I have a question about the iron lines. you said that you can infer how far away the inner edge of the disk was, and that this ion line was coming from probably material in the inner edge of the disk. I want to know, how do you infer the distance to the inner edge of the disk from this X-ray observation?
This is from the relativistic Doppler broadening of the line. So the closer to the neutron star you are, the stronger the Doppler broadening of any emission in the disk is. And there are some relativistic effects that, that boost that. And so you can look at the width of the ion line and from that infer how far away it is. Now this depends on things like the spin of the compact object and the inclination angle of the accretion disk. And those are all things that we don't really know for this system, so there is quite a bit of uncertainty there. But in this case, this line was clearly not broadened, whereas in other observations from other systems, we see much more broadened lines.
Isn't there a tension between having a very high level of ionization and having the disk very far away?
Indeed, yeah. When the disk is further away, the illuminating flux should drop. One suggestion that David Valentine made for our discussion was that he thinks that maybe it's not the inner disk itself that is reflecting, but some kind of low density material, still optically thick, close to the inner edge. You might imagine that if the inner disk is being truncated by a strong magnetic field, then from that truncation point, material still flows into onto the neutron star somehow. So from that, from the inner disk, there must be some kind of low density flow coming in. And so his suggestion was that maybe close to the inner disk, that material is still optically thick, so it can still reflect, but it's low density and therefore might produce a high ionization parameter.
Okay, thank you. So if there are no more questions, and let's thank the speaker again.
Thank you.